In this video, we will be looking at the teacher's notes for lesson 24. If you haven't already viewed the students' notes, then do so at this time. In lesson 24, we'll be talking about correlation coefficient, and we use lowercase r to represent that. Correlation coefficient is also called Pearson's R. That's the more formal name. There's several correlation coefficients, and the default, when you hear R in general, they're speaking of Pearson's R. It's named for Karl Pearson. He's a British statistician, late 19th, early 20th century. He's one of the most influential statisticians in history. When you perform the regression on the calculator on a TI-84, in addition to reporting R, it will report R squared. R squared is called the coefficient of determination. It's the fraction of change in Y predicted by the change in X. It is literally the square of R. So if we had an R equal to 0.9, then R squared would be 0.81, and this is a percent, 81%. We would say 81% of the change in Y is predicted by the change in X. Likewise, we could say it's predicted by the model, the least squared regression line. Okay, how do we calculate R? Well, your student will exclusively use the calculator. If you want to really challenge your class and have them use this formula, well, this will show you how. Also, you should fully understand the formula. It'll develop your full understanding of correlation coefficient a little bit better. R will be equal to 1 divided by n minus 1, where this n is the sample size, times the sum of each x sub I minus x bar, that's the mean x, divided by the standard deviation of x, times those values for y. Note x bar and y bar, these are sample means. That is the mean of the x and the mean of the y. This S sub x is standard deviation. You can use the calculator to compute the standard deviation. Standard deviation is a measure of spread. You can think of it as a typical distance from the mean. As the x values are more spread out, the standard deviation will increase. As the standard deviation increases, since it's the denominator here, this quotient will decrease. The more spread out the values, the lower the correlation coefficient. Correlation coefficient is a measure of spread. It's a measure of the linear strength of the relationship. All right, let's examine one set of data. Let's say we have a perfectly linear situation, x and y. Let's say x is 1, 2, and 3. The corresponding y's are 4, 6, and 8. Well, hopefully you see this is linear. As the x increases by 1, y increases by 2. If we graph these, it would be a perfectly straight relationship. Thus, R will be 1. Well, I will show using the calculator or using the formula how we will arrive at that. So note in the formula that we need the difference between each x value and the mean, the difference between each y value and the mean. So let us calculate both of those means. The mean x, if we add all those together, we get 6. 6 divided 3 is 2. This makes sense because this data here is symmetric. This middle value would be the mean and the median. Likewise for our y's, 4, 6, and 8, the mean there is 6. Okay, I'm going to add a couple columns to my table here. I'm going to calculate each x minus that mean value, and I will separately calculate each y minus that mean value. Okay, so our x bar is 2. Alright, x bar is 2. So our first x1 minus that 2 is negative 1. Our second x2 minus that 2 is 0. Our third x3 minus 2, our mean, is 1. Notice if we sum up these differences, they'll sum to 0. That's always the case with regards to the mean. The mean is this special number that takes all of the differences, and if you sum them, they'll sum to 0. Try it with some other value and you will verify that. Y bar here is 6, so our y bar is 6. I'm going to take each of my y's and subtract, and each y minus 6. So 4 minus 6, negative 2. 6 minus 6 is 0. And 8 minus 6, positive 2. Again, we see this summing to 0. Alright. We also need standard deviation of x and y. Well, the standard deviation of x, you can use your calculator to find that. One variable stats, it is 1. The standard deviation of y, it is 2. And these values make sense in the context of our definition here, or quasi-definition, a typical distance from the mean. If you look at these values, to say they're typically 1 from the mean is a reasonable reflection of that. Same way with this standard deviation of y. Okay. So now to our formula. The formula states that r is going to equal 1 divided by n minus 1 times the sum of each x value minus its associated mean divided by the standard deviation of the x's times each y minus the mean y divided by the standard deviation of y. Alright, so for us, 1 divided by n minus 1, well, our n is 3, that's our sample size, times the sum of, okay, x, the first x minus the mean, well, that we calculated that value here, it was negative 1. Standard deviation of x, that's 1. Times that same y value, y minus y bar minus 2, divided by our standard deviation of y, 2, plus our next x minus x bar is 0. Well, we know since the numerator is 0, this quotient will be, but our standard deviation is 1 there. Likewise for our y, 0 over 2. Lastly, the final x minus its mean, 1 here, divided by the standard deviation, still 1. Final y difference, 2, divided by the standard deviation there. Alright. 1 over 2, sum of, this is negative 1, this is negative 1, that product is a positive 1. Of course we have 0 here. Positive 1 times positive 1, again positive 1. 1/2 times this sum is 2, and half of 2 is indeed 1. So we see that r is 1 as we knew in the beginning. Okay. Let's talk about some special cases of r that aren't going to come up with real data but will potentially help your understanding. Special cases. if you have data that happen to be perfectly in a horizontal arrangement like this, all right, straight line horizontal, well, you can see here that there is no variation in terms of the y value. The x varies, but the y is all the same. Since the y is all the same, you would have a spread, a standard deviation of y that's equal to 0. Standard deviation equals 0 when all of the values are the same. And in this case, all of these y values are the same. So if we were to have a 0 in the denominator, our r would be undefined. In this case, r is undefined. Likewise, if you had strictly a vertical arrangement, we would have the same situation. R would also be undefined because in this case we have the standard deviation of the x values is going to be 0. That is, each one of these points would have exactly the same x value. Thus, standard deviation of x is 0. We're dividing by 0. R would again be undefined. If you have the strictly horizontal or strictly vertical arrangement, the correlation coefficient is undefined. Well, when do we get a correlation coefficient of 0? If you were to have some kind of arrangement where you would have this, where we would have both a change in x and both a change in y. You could imagine a trend line here that would be totally horizontal. Okay, in this case you would get an r of 0. All right. Likewise, if you had a vertical, and these aren't the only situations where you would get, do a better job of this. Okay, I mean, for that point to be in a vertical line there. Again, you students might think, hey, my trend line needs to be vertical. Well, the trend line would again be horizontal if we found one. All right, but in this case we would have a r that is equal to 0. Any of these cases, all of these cases here are going to be essentially contrived. Real data will not occur in that manner. In fact, our real data, even when it is no correlation, we would say we might have some kind of shotgun blast type situation. This is your standard, what you've told your students is no correlation. And we would indeed say something like this is no correlation, but it is highly unlikely. In this case, r is not going to be exactly 0, almost certainly. It's going to be some number very close to 0. But to say this is no correlation is perfectly okay. It would be, the r value would calculate to be not exactly 0, but very close. But when we call something like this no correlation, that's a legitimate way to say it. To say it's virtually no correlation might be more precise. But the bottom line is here is that while you might not get an r of exactly 0, to get an r very close to 0, it would be perfectly okay to say that there is no correlation. All right. Some additional resources that will be helpful for you. First, the Wikipedia correlation coefficient article. I suggest you show this to the students right along with the video. We're going to take a quick look at that page. Correlation coefficient. When you select the first Wikipedia hit, what you'll see is it gives you several kinds of correlation coefficients because there are. The top one, the Pearson product moment correlation coefficient, or R, or CAP-R, or Pearson's R, as I mentioned previously. So this is the technical name. As you can see, it's a mouthful. We will just call it R. Okay, you click on that. what is of interest to your students there. They can certainly read all that if you would like for them to, but this diagram will show them various correlations between 1 and -1. This will help them get a good idea of what that looks like. And here you see various kinds of zeros. And these, as you could tell, there's going to be virtually no time that actual data will appear in this fashion. And here you can see the horizontal arrangement that I mentioned before, and there is no number listed there. That is, this is undefined. Okay. Now, for my money, if I only had 5 minutes to talk about correlation with the students, what would I do? I would bring them to this last link here. Guess the correlation applet, Rossmann Chance. These are two statisticians who have done a lot of work recently with regards to statistics education. So Google guess the correlation applet. Your first hit, Rossmann Chance here. Click on this and you're going to see this screen. This screen, you're simply going to generate some random data and have the students guess the correlation. So the default number of points is 25. You hit new sample and it throws some points up there. And then you just throw it out to your kids and say, hey, what do you think this correlation is? Hopefully they can see that there is a slight negative trend here, and then just have some student take a guess at it. It's negative 0.392. I guessed negative 0.3. New sample. And you can have your entire class. I could do a class of 25 students in much less than 10 minutes. All right, so I strongly suggest having your entire class guess at this. In this case, it is negative again, but you can see it's tighter than the previous one, so it's going to have a greater absolute value that is closer to -1, maybe negative 0.6, negative 0.592, and you will just continue with this. This time positive, fairly strong. I might guess positive 0.7. Positive 0.718, and you do that through 25, and your students will be relative experts at guessing the correlation. We are good as humans. We are really good at seeing patterns, even when they don't exist. So that this will really help them understand. Also, in this, you can track performance, and then it will plot how the students' guesses look versus the actual, so you can get an idea. Are we guessing high? Are we guessing low? Does it appear that we're randomly scattered, which I will predict will be the case for your students after they do it for a little while. Alright, that concludes this video. One final note with regards to strength. The TEKS directly ask us to interpret R in terms of the strength. Well, I'm going to give you these three terms. Alright, with regards to the strength, we can say that it is strong, it is moderate, or it is weak. Lastly, we could say no correlation. For no correlation. Now, weak and no correlation, they will sort of blend together. In fact, all of these will. If we consider the number line momentarily, we have -1 here, 0 here, and 1 over here. If we have numbers very close to -1 and 1, we can call them strong. If they're in the middle, we can call them moderate. If they're closer to 0, we would say weak or no correlation. Now, the truth is that These terms, strong, moderate, weak, and no correlation, it'll be entirely a matter of context. For instance, you could have a number fairly close to 0, like R of 0.2 and R of 0.3. If you had an R, say, of 0.2, that would give you an R squared of 0.04. That might be strong if you were, say, a stock analyst, and you noticed between some predictor in the market and how the S&P 500 performed, if you notice there was a 0.2 correlation, that might be enough to beat the market and make your hedge fund all kinds of money. So an R of 0.2 in that context might be considered strong. Likewise, if you were an engineer and you were looking at how temperatures and tensile strengths of certain metals were related, in that case, an R of 0.98 might not be enough. You might need a much better relationship than that. So what is strong, moderate, and weak is entirely a function of the context. But for our students, that's going to be unsatisfactory to them. They need something to hold on to. So that something is these three words. And what I would do is go back to this applet again. Go back to the Rossmann Chance applet and just ask them to, before they even guess R, to consider how they feel about that particular relationship, just looking at it. So back to the applet. Generate some data. And ask them, what do you think about this relationship? Clearly they can see it's a linear form, and clearly it's negative. Do they feel this is strong, moderate, or weak? Well, probably no student's going to call it strong. Might they call it moderate? Sure. Might they call it weak? That's not unreasonable. So they take their guess. Maybe it's negative 0.5. And it is that. So now that they see that is it negative 0.505, are they more convinced that this is moderate or more convinced that it's weak? It really, quite frankly, it does not concern me. They whether or not they're able to attach that exact word to it, because there's ambiguity to those terms, strong, moderate, and weak. So have them look at plenty of this data, have them consider, do they think it's strong, moderate, weak, have them fire some numbers in there, and by the end they'll have while they might not all agree that this is moderate or all agree that this is weak, I would suggest they shouldn't all agree, and as long as they're able to have some intuition about what that is, that'll be satisfactory.